Hello everyone. Till now we have seen one technique, that is your divide and conquer technique. Now the next technique we are going is decrease and conquer. In the name itself it is there, decrease and then conquer. Conquer is you have to get the solution. Decrease means you have to decrease the problem instance and then you have to get the solution. In this we have three different types, that is decrease by constant factor and variable size decrease. See here, decrease by constant. First we'll see decrease by constant. What do you mean by decrease by constant? Here you have to just decrease the size of the problem instance is reduced by some constant. Constant means on each iteration you have to just reduce the problem instant by the same constant. For example, here means usually we will take this constant is 1. Okay, you can just increase the constant also, there is no problem, but basically we'll be having means we have to decrease the problem size by 1. See, this is of problem size n. I'll decrease this problem by one size. One size means n minus 1. That is subproblem of size n minus 1. Then solution to the subproblem and then solution to your original problem. This is how, this is the given problem and you have to reduce this by constant 1 and then you have to get the solution for the subproblem and then for the original problem. This is your decrease by constant. For example, see, if I have a function f of n is equals to a power n, then how will I just divide this one? I'll just divide this using decrease and conquer technique. F of n minus 1 into a. If n is greater than 1, if n is equals to 1, then it will be only a. This is how you have to just reduce the problem statement. Okay, you can do it. You can do this by using top-down approach or bottom-up approach. Both are same. Okay. His next technique is your decrease by constant factor. Decrease by constant is different and decrease by constant factor is different. Decrease by constant factor means here in this technique we just reduce a problem instance by the same constant factor on each iteration of the algorithm. On each iteration of the algorithm. Okay, here the most applications we use constant factor as 2. In decrease by constant factor, we have to decrease the problem statement by exactly half, as you will do in your divide and conquer technique. This is problem of size n, then subproblem n by 2. That n by 2 again we have to keep as it is, then solution for that and solution for the original problem. For example, if I have a function f of n is equals to a power n, here in decrease by constant factor, how will I just solve this one? Here you can just reduce it by half, is it not? So what you have to do, if you have a even positive number, then this will be divided as a n by 2, that is half whole power 2. Okay, if it is even number. Then if it is an odd number, then a power n minus 1 divided by 2 whole square. If n is equals to 1, then that is a. If n is odd, this is if n is even. This is your decrease by constant factor. And the last one is your decrease variable size decrease. The third one, variable size decrease. In the name itself it is there, variable by variable size decrease. Here in this method, the variable size decrease, in each iteration the size reduction pattern varies from one iteration of the algorithm to another iteration. For example, in the first iteration I'll just reduce it by 1, and in the second iteration I may reduce it by 2 or 3, and in the third iteration I may reduce it by 5 or 6, or again it may be 1 also. That this depends on the algorithm. This is called as your variable size decrease. The best example for this variable size decrease is your GCD of m comma n. Here also the value of m and n, the decrease depends on the values of m and n. If it is so big, it will be decreased one after the another. So we have to decrease variable size decrease will use in GCD of m comma n. Okay, this is the variable size decrease. This is your decrease and conquer technique. 3 methods you have. And this, the example of this decrease and conquer technique is, we have one example called as topological sorting. Topological sorting. What do you mean by this topological sorting? Actually, in the name itself it is there, it is a sorting technique. Yes, what do you mean by sorting? You have to just sort the given element in either ascending order or descending order. In topological sorting, usually we'll use a graph with vertices and edges. A graph means you will be having so many vertices. These vertices has to be ordered. It means the linear ordering of the vertices in a graph with respect to every edge is called as your topological sorting. See, for example, if I have a graph A, B, C, then D. Now you have to just topologically sort these vertex according to their edges. And here one more thing you have to remember, if you want to apply the topological sorting technique for any of the graph, this graph should be always directed acyclic graph. Directed acyclic graph. Here you see there is a graph, so you cannot just form a topological sorting for this one. It should be directed acyclic graph. It should not contain cycles, and always it should be a directed graph. Now we'll see how you have to do the topological sorting problem. Fine. Here, to do this topological sorting problem, we have two methods. One is source removal method. Source removal method, and the second method is DFS method. These are very important, source removal method and DFS method. First, I'll go for your source removal method. What do you mean by this source removal method first? In this method, a vertex which is not having any incoming edges is to be selected, and that has to be deleted along with its outgoing edges. Okay, if there are several vertices with no incoming edges, means arbitrarily a vertex is selected. Means always if you have 1, 2, 3, 4, 5, 6, among this 1, 5 and 6 are not having any incoming vertices. So first you have to select 1, then 5, then 6. In a linear order you have to select, and then you have to remove. Okay. The order in which the vertices are visited and deleted one by one is called as your topological sorting. For example, if you select the second vertex first and you remove, first I'll write 2, then the fourth vertex, then 4, then 5, then 1, like that we are going to just write the topological sorting of that one. First, I'll consider one simple example for this. See, I'll just take one graph. I'll just write one graph. This is called as a pendant vertex. This is allowed because this is not a cycle. Yes, see here, I have a graph over here. If you want to remove the vertex, then what is the first condition you have to remember? The vertex should not have the incoming edge. See here, D is not having any incoming edge. then A is not having any incoming edge, E is not having any incoming edge, and H is also not having any incoming edge. But according to the linearity, arbitrarily we have to go, which is the first alphabet it will come, that is A. So first what you have to do, you have to delete A. Delete A, and the corresponding outgoing edges also have to be removed. If I remove A, then how will be my graph now? This F remains as it is, F to G, G to I, then towards H, this remains as it is, then towards F I have B, next A I have already deleted, so I have B to C, then D, then E. The very first vertex I have deleted is A, because this is not having any incoming vertices. And then here you see B is not having any incoming vertex now, only two outgoing vertices, edges are there. Then D is not having any incoming, E and H. According to arbitrary thing means we have to just delete B now. Yes, I'll just delete D. Delete B. If you delete B, then how will be your graph? The two outgoing edges also will be deleted. I'll just get F to G, then this is I, I'll keep as it is, H again I'll keep as it is. Yes, then B I have removed, so C it will be as it is, D, then E. Okay, now you see this graph now, here in this graph, C it is having an incoming edge, so you cannot remove C. D is not having any incoming edge, E is not having any incoming edge, and H is not having any incoming edge. Now which one you have to delete? This is second deletion. Okay, now third deletion according to arbitrarily means delete D. Delete D. If you delete D, what is the graph you will get? I have deleted D, then incoming edge also will be, outgoing edge from D also will be deleted. C and E will be remain as the pendant vertices. I have just deleted D. Now see here, C is not having any incoming edge and E is not having any incoming edge. First, according to our arbitrary thing means, first you have to delete C. If I delete C, which graph you will get? This remains as it is. Then this E will remain as it is. Okay, now here H is not having any incoming edge and E is not having any incoming edge. So which one you have to delete? Among these two, first E will come. So delete E. If I delete E, which graph I'll get? F, G, I, then H. See here, F is having an incoming edge from H, I is having incoming edge, G is having incoming edge, but H is not having any incoming edge. It is having only two outgoing edges. So for which one you have to delete now? 6. Delete H. If I delete H, what you'll get? F, G, then I, because these two edges will get deleted with this vertex H. Now which is not having any vertex, not having any incoming vertex? See, F is having only outgoing, I is also having only outgoing. Which one will come first? First F will come. So I'll just delete F. So if I delete F, G and I will be left out. Next, G is having incoming edge, but I is not having any edges. So delete I. If I delete I, what you'll get? Only G. Then at last delete G. Now this is your source removal method. See here, so I'll just explain it once again. Source removal method, you have to just remove the vertex which is not having any incoming edges. If two or more vertices are not having any incoming edges, means you have to select the vertices arbitrarily according to their order. See here, A, D, E and H are not having any incoming edges, but first according to the arbitrary order, A will come. I'll just remove A and the corresponding edges also should be removed. I have removed A and I got this graph. After this, B is not having any incoming edge, so I have removed B, then D, then C, then E, then H, F, I and then G. In this order, I have to just write the things. Means in a topological order, I have to just write all the things in topological order. How will you just write this in a topological order? The topological sequence will be given as your topological sequence. First, which one you have removed? A. Then what is the 2? That is B. Then what is 3? It is D. Then which is 4th? It is C. Then which is 5th? It is E. Then 6th H. Then 7th F. 8th it is I, and last 9th it is G. This is your topological sequence of the given graph using your source removal technique. Okay, this is your source removal technique for topological sorting. Next, which is the second method? Actually, second method is the DFS method. For this DFS method, we need to use the stack concept. Okay, first in, last out, the stack concept. I'll just explain you this DFS method. Okay, see here. DFS method. I'll just take the graph . Yes, this is the graph we have for your DFS method. In this DFS method, you have to just follow some steps. The very first step is you have to select any one vertex as the arbitrary vertex. Among these vertex, any one vertex you can select as a arbitrary vertex. Usually we'll select the first vertex as the arbitrary vertex. Okay. Once a vertex is visited for the first time, then that vertex has to be pushed onto the stack. If this vertex is visited, means you have to mark it as visited. How will you just mark it? On pushing onto the stack, we'll mark this as visited. Okay, when a vertex becomes the dead end, then that vertex has to be removed from the stack. See, for example, from A we have a path to go to C and B. Is it not? Yes, from B I have a path to G and E. From G I have a path to F. But from F there is no outgoing edges. Then you have to remove this F from the stack. Okay, like that you have to just do this one. Then you have to repeat this step for all the vertices. Fine, you have to just repeat this step for all the vertices. Just a second, I'll just write a table and then I'll just explain you how you have to do this DFS method. This is the table we have for your DFS method. This is the graph what we have taken for the DFS method, and this is the table we have. I have already told you you have to use a stack concept to solve this DFS method. So here you see, first what you have to do, the very first step, you have to select any one vertex as a arbitrary vertex. Is it not? I have just told you I will just select for the first vertex itself as the arbitrary vertex. See, it is stack V is equals to adjacent S of top. If any adjacent vertices are there, then you have to mark it as S of top. Then nodes visited, I'll just take it as yes, and if the nodes is not having any adjacent vertices, then you have to just pop that from the stack. Okay, now I'm taking the arbitrary vertex A first. In the initial step you should not take any of the adjacent vertex or anything. First you have to take A as a arbitrary vertex. That's it. Now in the second step, which is on top of the stack, here node A is on top of the stack. Now you have to go for the adjacency vertices. See, from A there are two adjacent vertices. From A there are two. How you will find out the adjacent vertices? From A there should be a outgoing edge. There are two outgoing edges from vertex A. So A is having two adjacency vertices, that is B and C. According to arbitrary condition, first I will select B and then we'll come for C. Okay. First I will select B here. See, on top of the stack in the beginning A is there. So I'll just write B. Okay. Then now here nodes visited. I have already visited A and now I have visited B. Here I'm not going to pop anything. Okay. Now here, which is on top of the stack? See, B is on top of the stack. So I'll just take A comma B. Now you have to search for the adjacent vertices of B. See, B. How many outgoing edges? 1 and 2 towards E and towards G. According to the condition, first I have to take E. I'll just take E. The adjacent vertex of B is E. Now, what are all the nodes visited? A, B, already it is visited. Now, I am visiting this E. Okay. Now, pop nothing. Now, which is on top of the stack? E is on top of the stack. I'll just take A, B and then E. See, E. Is there any outgoing edges? No. If no outgoing edges means there is no adjacency adjacent. What is this for? E. In this case, what you have to do, you have to just pop E from the stack. Is there any adjacency vertex? No. Nodes visited, it will remain as it is, A, B and E. Now you have to pop E. The first element I have popped is E. If I popped E means what will be on top of the stack? This E is popped from the stack. So A comma B will be on top of the stack. Again I'll go to B. Is there any other adjacent vertex for B? Yes. It is G. So next adjacency vertex is G. Now nodes visited is A, B, E and G. Is there anything to pop? No. Now you have to check for G. See, A, B, G. Now on top of the stack, which is there? G is there. You have to check, is there any adjacency vertex for G? There is only one outgoing edge. So F is the adjacent vertex for G. I'll just take F over here. Now here it should be A, B, E, G and then F. Nothing to pop. So here A, B, G and F. For F, is there any outgoing edge? Yes, here no, there is no outgoing edge for F. So here there is no adjacency vertex for F. I'll just do like this, and then here nodes visited A, B, E, G, F. I have to pop F. If there is no adjacency vertices, you have to pop. Okay, now what will be there on the stack? A, B and G. Again I'll come back to G. Is there any other vertices which is adjacent to G? No, there is only one outgoing edge to F. So again there is no adjacency vertex. This one will remain as it is. Now what you have to do, no adjacency vertex means pop G. I have popped G. Now what will be there on top of the stack? A comma B. Yes, again I'll go back to B. See, I'll go back to B. Is there any other adjacency vertices other than E? For B, E and G, it is already done. There is no adjacency vertex for B. Again, what you pop B from top of the stack. I'll just remove B. Now only A will be remain on top of the stack. Again I'll go back to A, and one more outgoing edge, that is C, is there. So for this, what is here, there is a adjacency vertex. It will check B is popped. Now only A will be remain on top of the stack. Again I'll go to A in the graph. So see here, A, there are two outgoing edges, means two adjacency matrices, that is from A to B. A to B is already done. Next is A to C. C is not visited. You have to check in the visited list. So next adjacency vertex I'll just take as C. Now nodes visited A, B, E, G, F. Now the new is C. There is no vertex to pop. Now what will be on top of the stack? Now new vertex C will be on top of the stack. You have to check for C, is there any adjacency vertex? See, F is adjacency vertex, but F is already visited. If it is already visited, you should not consider that vertex. Okay, now for C, other than F, is there any other adjacency vertices? No, there is no adjacency vertices for C. So what you have to do, no adjacency vertex, this will be as it is. Then pop C. I'll pop C. Okay, if I pop C, what will be there on top of the stack? A will be there on top of the stack. For A, other than B and C, is there any other adjacency vertex? No, there is no adjacency vertex for A. There is no adjacency vertex. So A, B, E, G, F, C. Then pop A. No adjacency vertex means you have to pop. See here, how many vertex we have? A, B, E, F, G, C. Which is missing? D is missing. From all these vertices, there is no outgoing edge for D. So this is not visited, but you should not leave any of the vertices on writing the topological sorting. So what you have to do, see, if stack is empty, so take the next vertex in sequence which is not visited. Here which is not visited, D is not visited, and push on to the stack. Okay, I'll just push D onto the stack. How many adjacency vertices are there for D? A, B, F, G and C. But all these are visited. So I'll consider there is no adjacency vertex for D. Which are all visited now? A, B, E, G, F, C and also D. Is it not? Yes. So in the next step, what you have to do? You have to just pop this D. I pop D. Now here what you got? The pop sequence. This is not your topological sorting order. This is your popped sequence. Okay. This is the popped sequence. What is the popped sequence? E, then F, then G, B, C, A and then D. Topological order means from reverse you have to write. That is the topological order of your graph. Then topological order is first D, A, C, then B, then G, F, and then E. This is the topological order. This is the popped sequence, and this is the topological order. From reverse till beginning, you have to just write this is DFS method. See, I'll just tell you one more time. A, I'll take as arbitrary vertex. Then you have to check for the adjacency vertex B and C. According to the rule, we have to first take B. I'll take B as visited. Then A and B is visited. From B, again you have to search for the next adjacency vertex. B is having two adjacency vertices, E and G. According to this one, first I'll take E. So E I'll take. Okay, and for E, I have to search, is there any adjacency vertices? No, there is no adjacency vertex for E, so I'm popping E. Next, if I pop E, again on top of the stack, B will be there. B, again one more adjacency vertex is there, that is G. Okay, yes, now I'll just go with G. Is there any adjacency vertex for G? Yes, F is there. I'll just write that one. Okay, then for F, I'll search. For F, there is no adjacency vertex, so I'll just pop F. F is popped means again I'll go back to G. For G, only one adjacency vertex, so again G also will be popped. Okay, if G is also popped means I'll go to B. For B, there are two, E and G. Already we have done with E and G, so pop B also. If B is popped, A will remain on the stack. I'll go to A. Apart from B, you have one more adjacency vertex to A, that is C. I'll just write that one. Okay, I'll mark C as visited. Then A comma C, that is here C. You have to check, is there any adjacency vertex for C? Yes, F, but it is already visited. Visited vertex you should not take, so I'll just pop C. Okay, and then if I pop C, A is left out. For A other than B and C, there is no adjacency vertex, so pop A also. Here in first step, I'll just leave it as it is. Then in the second step, I'll just write A, B, E, G, F, C and D. Then here you have to pop D. This is the popped sequence. What we have, E, F, G, B, C, A and D. Then this is the topological order. From upside down you have to write from the down. D, A, C, B, G, F, E. Okay, this is your DFS method. It is very important. And in the next video, I'll come up with one more technique that is called as greedy technique. Thank you.